Hello, welcome back to physics. We're going to work on what we're calling free fall problems with constant acceleration, but in reality this type of problem isn't just involving free fall, it involves a rocket, which is going to have a free fall component. But when you think about it, when a rocket launches off a launch pad, the thrust is pushing the thing up. But even as the thrust is pushing it up from the engine, gravity is still pulling on that rocket down during that time. It's exerting a force. And the engines can overcome that to make movement off of the ground. But eventually, the engines will stop burning, right? They'll cut off, right? So what we say, I used to work in the space shuttle program for many years. So when we have engines, main engines, what we call them, the main engines, when we get to a certain height and then the engines cut off, we call it main engine cutoff, right? So we call it Mako, main engine cutoff. So I'm going to use that term a lot in here because we actually need to, it's not just to talk about something neat. It's because we're actually going to do a problem that involves a rocket that launches off the ground, the engine's cut off, so we call that Mako when the engine cuts off, main engine cutoff. But after the engine's cut off, the rocket has a lot of velocity. So it's like throwing a rock in the air. Eventually the engine's cut off, but the rocket still goes up in the air and then eventually will fall back down to the ground. So it reaches some maximum height. So we're going to do a rocket problem here. This is when the problems start to get a little bit more challenging and we have to really break it up into pieces. And so I want to make sure you understand everything about this problem, but then we'll have another one similar to it, but slightly different in the next lesson so you get some more practice with it. You're almost guaranteed to have a problem, something like this on a test eventually in physics. So the problem goes like this. A rocket launches upward with initial velocity of 50 meters per second and a constant acceleration of 2.0 meters per second squared until the engine stops at 150 meters of altitude. And we have three questions. The first one is, what is the maximum height reached by the rocket? The second one is, how long does it take to reach that maximum height? And the third one is, how long is the rocket in the air? Now, we're going to have to assimilate all of this stuff, and we're going to have to draw not only one picture, but probably a couple of pictures. As you do more problems, you probably won't have to draw quite so much, but it's really important to draw pictures for this kind of problem because I didn't really tell you in here, and the problem isn't worded as such, but there really is like several little bitty problems that are neat, that are kind of built into this little problem, and we'll kind of see that as we do it. But it's helpful to draw little pictures as we go just to keep your mind straight. So we have a rocket. We know its initial velocity is 50. So right off the launch pad, we know its initial velocity. And we know its initial acceleration, or its constant acceleration. So every second that rocket is going faster, 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 just like rockets do, at 2 meters per second squared. But then eventually it runs out of gas, and only at 150 meters of altitude, in which case main engine cutoff happens. After that point, the rocket continues flying up because it has some velocity, as soon as the engine is cut off, it's still moving up. But gravity is at that point acting downward with 9.8 meters per second squared, slowing the rocket down until eventually it reaches a maximum height, and then it just accelerates down and hits the water or whatever you've launched from. So all of these little pieces, what is the maximum height reach? How long does it take to reach maximum height, and so on? We have to really think about how to go because it's not going to be a simple plug into the equation kind of situation. We'll have to find a few things along the way. All right, so we have a situation here where we have the ground, or I could put the launch pad, right? And let's go ahead and draw our nice handy dandy rocket. Let's do it right here. We'll make it so tall. We'll draw a little pointy end so you see I'm a very good artist. That's our rocket. All right, so what's going to happen is when we launch, this rocket is going to go up in the air. That's what the dotted line represents. And eventually it's going to reach some spot in the air where basically the rocket is going to run out of gas. So it's going to go up and then it's eventually going to run out of gas. So we're going to call that this point right here. But the rocket still has upward velocity, so it's just like throwing a baseball. It's still going to continue rising for a while, but eventually that rocket is going to reach some maximum height, in which case it's going to stop exactly at a velocity of 0, and gravity will then take over and then basically pull the thing down like this. So this is downward motion, this is upward motion like this. Now again, I need to tell you, I'm drawing this as it's an arc in 2 dimensions, but really we're saying the rocket is going straight up and then straight back down. I have to draw it separate like this so that I don't draw it on top of itself. So it's going straight up and straight down. It's not a 2-dimensional motion problem. It's going up and down. So this point here, this point right here, we call it Mako. which is main engine cutoff. And then over here, let's draw some numbers. Let's see what we know. The problem says a rocket launches upward with initial velocity of 50 meters a second. That means right off the launch pad, it has a velocity here. So let's draw some numbers right at this point. So we put a little arrow telling us that at that time, we know the initial velocity was 50.0, but I'm going to put 50 meters per second. That's the initial velocity off the launch pad. It also tells us it goes upward with an acceleration, constant acceleration, of a is equal to 2. That's 2.0, but here I'm going to, just for space, I'm going to put 2 meters per second squared. So that's the initial velocity and the initial acceleration here. Now notice it doesn't tell us, but whenever we're doing any kind of a free fall motion problem where the problem begins, when the motion starts, we call that spot our y equals 0 initial position point, y naught, right? So we also know, we're going to write it here, that y naught is equal to 0 meters. What that means is any distance the rocket climbs off the ground is going to be positive distance. And of course, if it could go below the ground, which it can't, but if it did, then that would be negative position. But so it's going to be positive displacement or positive position all the way around. So that's what we know from here. And then what do we know after main engine cutoff? So now the rocket is basically, the engines are shut off and now it's just purely coasting upward with, of course, gravity acting on it. So at this spot, whenever the cutoff happens, we have some new information, okay? First of all, we do not know what the velocity is at that point. That was not given to us. The problem says the rocket launches upward with 50 meters per second with a certain acceleration. Engine cutoff happens at a certain time. The problem doesn't tell us how fast the rocket is going at engine cutoff or anything. So all I'm going to do is put that I have no idea what the velocity is at this point. We're probably going to have to find it at some point throughout the problem. Right? But we do know what the acceleration of the rocket is after engine cutoff. Because when there's no engine acting and it's just like throwing a rock in the air, the acceleration is negative 9.8 meters per second squared. That's the acceleration of gravity. And we also know that when this motion starts, it's at a position of 150 meters off the ground because it says the engine stop at 150 meters of altitude. And since positive distances are up, I'm going to put it like this, 150 meters. So I know it's a little bit cluttered, but basically we have two pieces of information, and that's why it's really useful to to draw it here so that we can put the information that we know about launch, the velocity, the acceleration, and the position, and then we put the information that we know after engine cutoff, which is we have no idea what the velocity is. We know the acceleration, that's because of gravity, and we know how high it is off the ground. All right, but you can see from the fact that we have this drawing here that there's a clear break in this problem. You see, that's what I was trying to tell you without really telling you, because I don't want to give away the farm initially. I want to learn as we go, right? But there's really two problems inside of this problem. There's a problem with what's going on with the rocket before engine cutoff that we're going to end up using equations to solve, because the acceleration is 2 here, right? And then there's a kind of a separate problem. What happens after cutoff? That's going to be what's going on after cutoff. The acceleration is totally different there. So my rule of thumb that I want to teach you is that when you have a problem where the acceleration changes, like something's happening with some acceleration and then after some moment, then something else happens, and something changes and the acceleration is different, then what you really have is like two separate problems really going on. Because if you look at your equations of motion, there's one acceleration term here. This equation will tell you the velocity of something. When you know its starting velocity, you know the acceleration, and you know how long this acceleration was happening for, right? Or this equation will tell you how far something travels when you know its initial velocity, the acceleration, and the time that this acceleration was happening for, right? But when the acceleration changes, students try to use these equations and they can't. They don't know what to do because there's only one acceleration. So which one do you put in here? This one, or do you put this one? Well, you don't use the equation one time. You have to break the problem up into two problems. And the thing doesn't tell you that. Physics would be really easy if they would say, hey, there's a rocket, and before launch, you have to use the equations here for kind of like one part A, and then after cutoff, engine cutoff, you use the equations again for kind of like another part of the problem. Then it would be a lot simpler because they would guide you. But in physics, it's difficult because they don't guide you. So we draw the picture and we recognize that there's really a part one of the problem and there's really a part two of the problem. In fact, part two of the problem is so important that I'm going to actually draw it again over here. Right? So this is the ground I know I said launch pad, but whatever, launch pad's on the ground. So what we have is, after Mako, so let's put over here, we'll draw this, the title of this picture will be After Mako. Our second problem really boils down to the following. The rocket was basically up at this height, so I'll try to draw it like this. It's the same drawing. I'm not really doing anything different, but I want to make it absolutely clear. The rocket goes up, it stops, and it goes down and hits the ground. So this problem here, the after Mako problem, is exactly the same as the problem that we had when we were throwing the stones off the building. Because remember, we did a problem before. We were standing on the building at a certain height above the ground, I think 50 meters, I think it was, or something. We have a rock, and we throw it up, and we ask all kinds of questions. How high does the rock go? How long does it take the rock to get here? How fast is the rock traveling when it's 10 seconds later, or something like this? You see, that problem with the rock that you already know how to solve is exactly the same as the problem with the rocket after engine cutoff. The only difference is we haven't yet figured out how fast the rock's going. I mean, the rocket. We don't know how fast the rocket's going at cutoff. But other than that, they're the same, because this is basically a free fall problem. The rocket has an initial velocity that we're going to end up finding, but it has an initial velocity, and gravity is acting down the whole time, slowing it down and so on, and we can figure out everything we want to know about the rocket. So I want to draw it so you understand where we're going. So it's really like two problems in one. So we need to make some progress here. We want to figure out what is the maximum height reached. That's part A. When we say maximum height, that means the very tippy top of this. So we actually know something about the tippy top of this. We know that at the very top of the motion, the velocity is equal to 0 because it just stops and then it starts falling. Same thing here, it's the same drawing. So we can say the velocity at the very top is equal to 0. So we know something about the top as well. So the question is, how do we figure out the maximum height reach above the ground? Well, again, there's two parts of the problem. Let's pick a roadmap. What we're going to do is try to figure out what is happening with the rocket as it launches all the way up to cutoff. And specifically, well, let's figure out how fast the rocket is going right there at cutoff, at this moment, or I guess at this moment when the rocket and the engine's cut off. The reason we want to figure that out is because we know that if we know the velocity at cutoff, then it becomes a free fall problem, and we can calculate the rest of the motion as it goes up to a stop, because we've done that in previous problems, and then we'll basically know how high the rocket reached. And also, if you read the problem, it says the engines stop at 150 meters of altitude. So we actually know this distance right here from engine cutoff to the ground is 150 meters. So we know that. So what we'll do is we'll figure out how fast is the rocket going here. Then we'll use the equations to figure out how high it travels from this point. And then we'll just add that distance to the 150. That'll be the total height of the rocket that it's traveled. All right, so let's go over here to part A and do that. So we'll say before Mako, which is main engine cutoff, right? This is before the engine cutoff. So what we're going to do is we're going to figure out, before we do anything else, what is the velocity at Mako? And let me tell you one more thing before we actually do this. I've laid out a roadmap for you so that you understand why we need to know the velocity at engine cutoff, right? But let's say that you don't remember that, or let's say that you just have no idea what to find, right? That's when problems like this get people stuck, right? So in that point, what you need to do is, if you don't know what to do, if you have no roadmap at all, what you need to do is look and say, these are two problems. I have a part A and a part B. I need to figure out everything I can at the moment of cutoff, because that's going to feed into the second part of the problem as the initial conditions into the second part. I know the initial velocity off the pad. I know the acceleration. I know the distance to 150 meters because that's the height at cutoff. The only thing left to find is how fast the thing is going. So find it. Find whatever you can, I guess is what I'm trying to say, at main engine cutoff, and then go back and look and see what you know again to figure out the next piece of the puzzle. So if you get stuck and you don't have a roadmap, just find what you can. That's kind of the bottom line. So what is the velocity at Mako? What equation are we going to use? I'm going to write it down and you'll see why we can use this guy. The final velocity squared is the initial velocity squared plus 2 times a times y minus y naught. Now there's always more than one way to solve a problem, but the reason we're going to do this one is because we know the initial velocity, we know the acceleration of the rocket, and we know how far the rocket travels because it tells us 150 meters off the launch pad. So we look at our equations and we say we know how to use this one. And we say, all right, final velocity squared. What is the initial velocity? It was 50 meters per second up so it's positive here, plus 2 times a. Now usually for a we put 9.8 meters per second, but it tells us the rocket is accelerating up at 2 meters a second. So that's the acceleration we have to put here, 2.0. It has to be positive because it's actually accelerating upward, right? And then what do we put for y minus y naught? Well, y naught is going to be the initial position of the rocket, which will be 0. And the final position of the rocket at the conclusion of the motion is 150 meters positive in the air. So it's final position minus initial position. This is 150 above 0 minus 0. And we have everything on the right-hand side as a number. So what you'll get is v squared is 2,500 when you square this term. When you multiply these things together, you'll get 600. And so what you're going to get is v squared is 3,100. And so what you're going to get is v is equal to 55.68 meters per second. And just to remind myself, this is the velocity at Mako. Right? I'm not going to circle it because it's not our answer. But I might put like a little asterisk or something so that I can easily find it again. So that's very, very important because from the knowledge that we know of the rocket and its acceleration, we now know how fast it's going at Mako. All right, which is 55.68 meters per second. Now, we now know the velocity here. So we had a question mark here. So now we know that this initial velocity is actually 55.68 meters per second. Right? That's an initial velocity. At the moment, the engine's cut off and it's going to coast until this velocity reaches 0, and then it's going to be a total free fall like a rock all the way until it hits the ground. Now, the next thing you should always do is try to figure out everything you can figure out. So let's figure out how long does it take to reach Mako in seconds. The problem never says how long does it take to reach Mako, but if you read ahead, it asks you in part B, how long does it take to reach maximum height? So that means we need to know how long does it take to reach Mako, and then how long does it take to reach from when Mako happens till it finally hits 0 speed. So you don't have to find this right now, but you know you're going to need to know how long it takes Mako to happen. So let's go ahead and do it as we were doing these other calculations. So how would we figure that out? So now we know the final velocity of the rocket. We just found it. It's 55.68 here. We know the initial velocity. We know the acceleration is 2, so now we can easily figure out how long it takes to reach Mako. So I will write time, whoops, if I can spell time, time to reach Mako. Time to reach Mako. So we're going to use our equation of v is equal to v naught plus acceleration times time. We know the final velocity. We just calculated it, 55.68. We know the initial velocity. That was given to us in the problem. That's 50 straight up. The acceleration of the rocket was 2 meters per second up, so it's positive. And then we're trying to calculate the time needed, basically for, whoops, not a plus here. This is an equal sign. The time needed for the velocity to go from here to here. That's essentially what you're doing. And so when you do this, you'll have 2 times t on one side of the equal sign. We'll subtract this, and you get 5.68. So the time, when you divide by 2 there, is going to be 2.84 seconds to Mako. Now again, this is not an answer, right? This is just something I know I'm going to need. So I'll put a little, maybe I'll put a little asterisk right there just to kind of help me find it in my notes later on. So we've actually made a lot of progress, even though we haven't even answered part A yet. Now we know how fast the rocket is going at main engine cutoff, and we also know how long it takes the rocket to go from launch all the way to cutoff. So we pretty much know everything about the motion during the powered flight phase when the rocket engine is still burning. So now here you have to think about what to do next. The problem is telling you that it wants you to find what is the maximum height, which means now we've already done the first part of the motion. Now we have this part. We have this motion here when the engine is stopped, and it's a totally separate problem, and the rocket is coasting upward like this. Now you have to make some decisions about how to handle it. There's lots of different ways to solve physics problems. My goal here is to teach you how I do it. I'm not telling you that my way is the best. I'm just telling you that it's my way, and you can hopefully learn something from it and find your own way. But what I think we should do is I look at this second part of the problem as like a totally separate problem. So if I had given you a problem, for instance, and I had said, let's just take another universe here. You'll understand why in just a second, why I'm going down this road. Let's say I give you another problem. It says, a rocket has been launched, right? At 150 meters in the air, the rocket is going 55.68 meters per second. How high above engine cutoff does the rocket travel before it, falls back down to the ground? Right? If you did that, then you would draw a picture just like this. You would never draw this picture here. You would draw this. You would say, well, it's 150 feet in the air, meters in the air, which I actually know. It's 150 meters in the air, right? And I know the velocity here, so you'd write that down. I'm not going to write it again because we already did. And you would do a free fall problem. You would say, well, what I'm going to do, almost certainly what you would do, this is what I've been teaching you to do, is you would define this point right here to be y naught is equal to 0. And you would say, well, okay, this is y naught, and I'm going to figure out how far above my reference point this thing goes until it hits rest, and then I'm going to add this number to this number, and that's going to tell me the total height reached. So that's what we're going to do. And the reason I presented it to you that way is so you could see that that's how you would have done it if I give you the simpler problem. Right? So now we're going to redefine things and say now at engine cutoff, it's a totally separate problem. Y naught is 0, and now we're going to find out how high the rocket goes above cutoff. Above cutoff. So what we're going to say is, let's see here. What are we going to do here? We're going to say at turnaround, in other words, when it does finally reach maximum height, the velocity is equal to 0, and we're going to try to calculate how high the rocket reaches from engine cutoff up to that point. So we're going to use the equation v squared is v naught squared plus 2 times a times y minus y naught. Why are we using this one? Because when you look at the other ones, you don't have enough information yet to put them in there. And so there are always other ways to solve the problem, but we have everything to do this one, so we're going to use this one. And so what we'll do is just say, what is the final velocity? Well, when you look here, we're basically trying to say, if the initial time is here, the initial velocity is here, the final velocity of the motion is up here at the very top of the arc, which is 0. The initial velocity we know, we just calculated it. So the final velocity to the top of the arc is 0. The initial velocity is 55.68, because we're kind of solving a totally secondary problem now, right? And then we say 2 times a. What is the acceleration now? Well, the rocket is no longer firing its engine, so the acceleration is just due to gravity, 9.8. But it's down. It acts downward. This velocity is upward, so that's why it has a positive sign. And then you have to figure out what to put in for this. Well, what is the final position going to be of the rocket at this motion? I don't know what that is. That's what I want to know, so I'm going to keep it there. What is the initial position of the rocket? We're saying it's 0. We're basically saying the rocket starts at a 0 position. I want to figure out what its final position is at the very top. How high above this starting point is it? So this is how high it travels above the starting point. This is the initial position. Everything else is just a number. So what I'm going to have is I'll have 0 equals 3100.26 for this term. When I multiply these together, I'm going to get negative 19.6 times y. And now I just solve for y. So y will be equal to negative 3100.26 divided by negative 19.6 when I just move this over and then divide. And so what I'm going to get is y is equal to 158.18 meters. Now, what does this mean? This is how high the rocket travels, but above Mako. Why? Because this is why you can't just plug things into physics equations, because when we solved it, we said this is our problem. It starts here. Its final position is here. So we weren't measuring the final position from the ground. We were measuring it from Mako. So the answer we get for y, 158.16 meters, was the distance above Mako to here. So we just need to add the 150 to it to find how high the rocket goes above the ground. So then we say total max height is going to be equal to 150 plus 158.18, which is going to be equal to 308.18 meters above ground, above the launch pad, whatever. This is the answer, 308 0.18 meters. And you can see that there's a lot of little steps here. And now you see why we did kind of simpler problems to begin with, because in physics a lot of times you'll just get one example, two examples, and then you'll get this on a test. And no one is going to do well on a problem like this without getting some practice and understanding how to do it. So we'll review everything at the end, but essentially we had to break it up into two problems, find the velocity at Mako, then treat it as a new problem to figure out how high the rocket rises above that, and then we add it to the height at Mako that we knew. Now, second part and the third part of the problem are much shorter because we've already calculated a lot of stuff. The second problem says, how long does it take to reach max height? How long does it take to reach max? That means how many seconds. Now, interestingly, way back here, we calculated this time that it took 2.84 seconds to reach Mako. Because remember, we knew we were going to need that. So this is the time it takes for the rocket to go 150 meters when the engine's cut off. So that's this time. Now we need to know this time. How long does it take to reach from here to the height? And then we'll just add it, the exact same thing. We'll add it to this time in order to figure that out. How do we figure out the time required here? If there was only an equation that we had that once we knew the initial and the final velocity, we could find the time. Well, if you know the initial velocity, the final velocity of something, and you know the acceleration, in this region it's just acting, gravity's acting on it, then we know all three of these numbers and we can figure out how long it takes for that to happen. So, we'll go down here and we will say the time from Mako, Mako, main engine cutoff, to maximum height. That's what we're trying to find. And we're just going to use our trusty equation. V is equal to V naught plus the acceleration times the time. Now, what is the final velocity? When it goes to max height, the final velocity is 0. The initial velocity, what is that? That's the velocity we calculated a long time ago, 55.68 meters a second. This is the velocity at Mako. So this is acting upwards, 55.68 meters per second. The acceleration after cutoff is just due to gravity, 9.8, and acting down, times time. So I trust that you all by now know that you can just move this over, it'll make it negative, and then you divide by a negative, so the answer you're going to get for time will be a positive, and it'll be 5.68. And the answer is going to be in seconds because you have meters per second everywhere. This is the time from Mako to max height, and we know already that the time from ground launch to Mako is this, so to find the total time to max height, we just add them together. So the total time to max height is just going to be 2.84, which is the time from launch to Mako, plus the 5.68, which is the time from Mako to max height. So what you're going to get when you add those together is 8.52 seconds. That's the total time that the rocket takes from launch all the way up to the top, some of which is powered flight and some of which is essentially free fall with an initial velocity until it finally reaches the end when it stops when the velocity is 0 at the top. So very much a problem with two kind of sub-problems. Now the last part of the problem says how long is the rocket in, sorry, that was the time to reach max height, that's what we did. The third part is how long is the rocket in the air? Now a rookie mistake or an inexperienced mistake would be to say, well, I just calculated how long it takes to get to the maximum height. That's 8.52 seconds. And I know that if I throw, what goes up must come down, so the time it takes to get to the top must just be the same as the time it takes to get to the bottom. So I'm going to take 8.52, I'm going to multiply it by 2, and that's going to be 16 or whatever, 17 point something seconds. That's the answer. But that's wrong, because it is true that if I throw something up, the time that it takes to go to the top is exactly the same as the time it takes to come down. That's all true. However, that's not this case, because for some of this motion, we were pushing on it with a very powerful rocket engine. So because we're pushing on it for some of the motion, their symmetry is lost here, and we're basically not going to take the same amount of time to reach the top as it is to come back down. So we need to calculate how long it takes the rocket to come from the top all the way to the ground in seconds, and then we'll just add that time to the total time that we calculated for the upward motion. That'll give us our total time. So the question is, how do you find how long it takes the rocket to go from here to here? Well, it's just a free fall problem. If I were to climb, how high do we say the rocket rises? 308.18 meters. That is the total height. If I built a ladder that high and dropped the rocket from there, then gravity would just pull it to the ground, and we can calculate how long it takes that to happen. It's just a free fall problem. And that's all. That's what we need to basically know. So we're using this 308.18, and we want to calculate how long does it take the rocket or any object to fall to the ground under the influence of gravity there. So for part C, that's what we need to do. We want to figure out how long that happens. And or how long it takes for that to happen. There's a couple of ways for that, for you to do that. There's a couple of ways for you to find that time. What I'm going to do is we know the total distance traveled. So let's go and that's going to be the distance is going to go feed into this part. We know the acceleration. We know the initial velocity is 0 here. So then we can calculate the final velocity of the rocket as it impacts the ground. Because we know everything on the right side of the equation here, we can find the final velocity here. Once we know the final velocity, we just feed it into this equation. Again, we know the initial velocity, we know the acceleration, then we can find the time. Another way to look at this is to say, well, if I drop a rock from here, how long does it take? I need to know the initial velocity, the final velocity, and the acceleration. Unfortunately, I don't know this final velocity, so let me find it first. So let's use this equation to find it first. It's a good example of in physics, often you just have to find some things before you find others. So let's first find the final velocity of the rocket as it impacts the ground. And that's going to be v squared is v naught squared plus 2 times a times y minus y naught. All right, so the final velocity is going to be the initial velocity. We're dropping it from a height, so it doesn't have any velocity. 2 times negative 9.8 because we have gravity acting on this thing. And then what did we put in for these? Well, again, you're redefining the problem yet again at this point. So let me go off to the side. Now you're changing it into a free fall problem. This is the ground right here. And we're basically saying here is a rocket. And we're basically saying y naught is equal to 0 up here. And we're just going to drop it. And it's going to go down, 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 down. And it's going to have some final velocity. And it's going to obviously has some initial velocity of equal to 0. And gravity is acting with negative 9.8. But you see, we're redefining the problem yet again. We're saying just to figure out how fast the thing goes, this is the starting point, this is the ending point. So the ending point here is going to be what? Well, let me do it this way to make it a little easier for you to understand. The starting point is y naught, which you all know is 0. That's where we start from. The ending point is below y naught, which means it has to be negative, and we already said it was 308.18. You have to get the signs right. Here. So it's very important to draw another picture so that you can then calculate. Now we have numbers everywhere, and then what we're going to have is v squared is equal to, on the right hand side we'll have 6040.33, and then the velocity you get when you take the square root will be 77.72 meters per second. You have to be a little careful here because when you take the square root, your calculator is always going to give you a positive number, but you know that this is going down. You know that this is going down because the rocket's obviously traveling down. So another way to say it is you really know that the velocity is negative 77.72 meters per second. Your calculator is going to give you the positive value, but you know when you take square roots in algebra, anytime you take square root of a number, there's always two answers. Like the square root of 4 can be 2, but it could also be minus 2 because negative 2 times negative 2 is also 4. So when you take the square root of this number, really you're getting two answers. And the negative answer is really the correct one because in physics, down velocity, that we know it's going down. So this is really the correct thing. But your calculator will give you a positive value, and that's why I put it there. You know the velocity is this number. You know it's acting down. So when we feed this into the next equation, you'll need to make sure that the correct sign is in there in order to get everything correct. So the next part of the problem is we want to find the time, right? So we're going to use v is equal to v naught plus acceleration times time. The final velocity of the rocket, the final velocity of this rocket, just feeding it in from here, is negative 77.72 with the correct sign, meaning it's going down. The initial velocity of the rocket is 0 at the top, plus the acceleration is negative 9.8, and then we have the time. And so then the time, when you divide, you're going to get a negative divided by a negative, So what you'll get is a positive 7.93 seconds. And then what is this time? This is the apex to ground. So the rocket has powered itself all the way to the top. Then it's like dropping a rock. It takes 7.93 seconds. And we already know from our previous answer, where did we say here? The total time to get to the top was 8.52 seconds. There. And then we then add these guys together. The time of flight, I'll call it. Or call it flight time. Because the problem is worded to say how long is the rocket, because it say how long is the rocket in the air, right? So what that's going to be is, it's going to be the 8.52 plus the 7.93. And when you add those guys together, you get 16.45 seconds. Now you see what I mean. In the problem here, there is an A, B, and a C, but really there's a bunch of other little subparts that you have to kind of figure out as you go along here. We're going to go through it really quickly as a summary, but I just need you to know that there's definitely more than one way to do it. So when you look at the solution and you say, well, why didn't you do it this way? Couldn't that have worked? Then work it out yourself. See if it does work. This is very likely that there's another way to do it that I just didn't do. That's fine. Do it that way as long as you're getting the right answer. So the first thing was to recognize that there's really two little problems in here. The problem during powered flight and then the part after Mako, after the engine's cut off, which is basically a free fall motion kind of problem. So the first step is to figure out everything we know during the powered flight part. So we figured out the velocity at Mako, right when the engine's cut off. We found that from this equation. We found out this was the final velocity there. And then the time required to lift off from that point, we used this equation to figure out this is how long it took to get to Mako. And then we said, well, from the point of Mako to the turnaround point is like another problem in and of itself with an initial velocity that we now know and a final velocity of 0. So we redefine the problem again just to figure out how long it takes, or I should say the height of there. Then we use this equation to put in everything we need. Initial velocity, which was the velocity at cutoff, and so on, and this y that we calculated was the height above the cutoff point in space, 158.18 meters above Mako. Then we add that to the 150 that was given in the problem when we reach cutoff. This is how high the rocket goes above the ground. All right? And the problem said, the next part said, how long does it take to reach max height? Okay? So then there's going to be two parts to that. We need to know how long is the powered flight phase, and then how long in seconds does it take to reach the top here. And so we already know the first part, we calculated the 2.84 seconds to Mako. So now we have to find the second part, time from Mako to max height. So we use this equation because we know the turnaround velocity is 0. We now know the initial velocity. We know the acceleration is negative, and we calculate the time and we add it to the 2.84, and that's what you get. You see, there's a lot of little things to do that aren't told to you. That's what you have to work through logically, is what needs to be done first, second, and third. Then for the third part, we wanted to find how long is the rocket in the air. Now we've calculated the time from powered flight and then up to the maximum height. We know how long that takes. Now we just have a rocket up there that we just drop, and gravity just lets it fall. So we redefine the problem again. We're starting at an initial position of 0, an initial velocity of 0. How long does it take to hit the ground? Well, the first thing we need to figure out is how fast is it going when it hits the ground. We can use this equation. We know the initial velocity, the acceleration, and the distance traveled, meaning the distance below the drop point, and the value, the drop point is at 0. Then we calculate the velocity at impact with the ground. But with square roots, you really have two answers, so we're really going to use the negative answer because we know the velocity is acting downward when it's going to hit the ground. So we take this and plug it into the next equation. Initial velocity, final velocity, acceleration time to find the time. This is the time it takes the rocket to hit the ground. We add it to the time that it takes for the rocket to go all the way to the top, and we get the total flight time of the rocket. Difficult problem, honestly, the first time you do it, because there's a lot of little pieces there. You need to get in the habit in physics of, if you don't really know how to get to the end, which nobody does. I didn't know how to get to the end of this problem when I read it, and I'm being honest with you. A lot of people say, well, this guy knows it. He's done this before. True. That's the reason I figured it out, because I've done it before. But even when I read this problem, I didn't know exactly what needs to be found. I did it exactly the way I'm showing you. I was like, well, I know this, so I can find this. And once I find this, I can find that. So that's what you have to do. So make sure you can do this yourself. Follow me on to the next one. We'll have another rocket problem, which will be not quite the same, but similar kind of thought process. And you need to get practice with it. So make sure you can solve this. Follow me on and get some more practice in the next lesson.